vertical circular motion. We'll take a look at what's happening just at the top and the bottom of this vertical circular motion. So let's solve for that. What's happening up top and what's happening at the bottom. Now first I want to draw a free body diagram. Now as the object circles around and is at the very top, there's two forces acting on it. Force due to gravity, pulling down of course, and the tension in the string that's moving it around. Round and round it goes. When it's at the bottom, force due to gravity of course can only be downwards. And since the mass is the same, the length of the arrow should be the same. Tension, is that going to be the same? Well, I'm going to think not, but I don't know for sure yet. That's what we're solving for. So this is a free body diagram. Step 1, free body diagram. Step 2, the F net statement that adds those forces together. And here they're in the same direction, so the F net is equal to the sum of the two. So here they're in opposite directions, and I'm going to make the claim that this tension is going to be larger than the force due to gravity, and I will go with, whenever I have a tug of war, a larger minus smaller. Works really well. I just have to consider magnitudes. Don't have to worry about plus minus for directions. So there's a start. Now, then I remind myself that in circular motion, the F net is the centripetal force. So let me just change this a little bit. Centripetal force is the tension plus the force due to gravity. Likewise here, just reassign that. Tension minus force due to gravity. Great. Next, so I'm looking for the tension in each case here, and so I'll isolate the tensions. Force tension is going to be equal to the force centripetal minus the force due to gravity. And over here, the tension in the string will equal the centripetal plus the force due to gravity. So a nice force analysis of a circular motion. Now let's take this a step further. Tension force, there is no specific equation for that, but for centripetal, I'm going to go with mv squared over r. Very common and popular formula for centripetal motion. Force due to gravity, as usual, m times g. And that'll be the case over here also. mv squared over r, but this time's plus the force due to gravity. Comparing these two side by side. Great. How about a substitution in the numbers? Look back at the question. Well, the mass in this case is 75 grams, so 0.075 kilograms, times the speed, we're told, of 3.80 meters per second. Let's square that. The radius, 85 centimeters. Change it to meters, do not forget. And then plus the force due to gravity, mass times 9.81. Let's run that through our calculator. So 3.8 squared times 0.075 equals, divided by 0.85 equals, and we have our answer there, 1.27. 1.27, I'll say 41 newtons, plus over here 9.81 times 0.075 equals, and 0.73. 0.73, oh, I'm going to say 575, going a bit overboard there, newtons. Now, that's nice, it's wonderful. Over here, those numbers haven't changed. mv squared over r, the force centripetal, is again going to be 1.2741 newtons. I don't have to run that through my calculator again. But this time we add 0.73575 newtons for the force due to gravity. So let's take a look at those and see what we have going on here. And oh, look at this, I made a mistake. From negative, I put a positive there. Bad, bad, bad. Well, I'm going to mention that mistake And that's okay. That's one good thing about showing a lot of work, like I'm doing here. Is if you make a careless error, like that certainly was, there's a much better chance of you finding it. If you're not writing a lot of stuff down and you make a mistake, less chance you finding it. Then you'll be sad. So subtract those two, 0.53835 newtons. Over here, 1.2741 plus 0.7375 equals, and over here at the bottom I get 2.00985 newtons. Fantastic. Now let's round those off to appropriate significant digits. So I'm going to say at the top, the tension in the string is 0.538 newtons. That's at the top. And at the bottom, the tension here is going to be 2.01 newtons. And there we have it. And if you were to take a mass on a string and whirl it in a vertical circle, you will notice that the tension is greater at the bottom than it is at the top. And we're done.